So 9.1, we want to talk about random variables and distributions. So we've seen that word distribution before when we were talking about probability functions and probability distributions. This is going to be that same type of thing, but now we're using the idea of a random variable. So let's unpack this definition. A random variable is a rule that assigns a number to each outcome of an experiment. So what does this mean? So it's a rule that assigns a number to each outcome of an experiment. Well, that sounds a lot like something we've studied before. So to remind us, the definition of a function is a function is a rule that assigns each input to exactly one output. So based on this definition, what is a random variable then? Well, random variable is just a function, right? It's just a rule that assigns a number to each output of an experiment. So then the domain of our rule, so the first thing, a random variable is a rule. So a random variable is a function. It's just a function. Its domain is going to be the sample space. And its range is just going to be real numbers. So the reason I want to emphasize this is it's going to seem like it's something crazy new and different. You know what functions are, we know how to use them. So don't let the fact that we're calling it a random variable bother you. It's a function. It's going to behave like a function. It's going to do the things that normal functions do. All right, so let's build on this a little bit more. So we have a couple of different types of random variables. So the first type of random variable we want to talk about is a discrete random variable. So a discrete random variable can only take on isolated numerical values. So that's going to be something like 1, 2, 3, 4, 5, but you can't take on things like 1.5. A continuous random variable can take on any values within a continuum or an interval. And we'll do some examples of each to help us see what the difference is. All right, so here's example number 1. And it is an example of a discrete random variable. The outcome of the roll of a die is a discrete random variable. If we have the experiment of flipping a coin, and define our rule to be x of tails equals -1 and x of h equals +1, then x is a discrete random variable. So in each of these cases, so if I roll a die, what are my 6 possible outcomes? 1 through 6. I can't roll a 2.5, right? I can roll a 2, I can roll a 3, but nothing in between. So it's a discrete random variable. The same thing with if I flip a coin. So my flip a coin, my 2 possible outcomes are heads or tails. If I assign tails the value of -1 and h the value, or heads the value of +1, then that's a discrete random variable because my outcomes are -1 and 1, right? So we're not getting things, once again, that are continuous in a chunk. So let's take a look at our next one. This is an example of a continuous random variable. So if we randomly select a person living on Earth and measure their height in centimeters, it's a continuous random variable. Because you can be 62.9999993 centimeters tall, right? If you have an accurate enough measuring tool, it goes as accurate as we wish, right? So there is no discreteness. You don't go from 60 centimeters tall to 61 centimeters tall, right? You have to go through all of the values in between. So that is an example of a continuum, which would be, I don't know what the shortest person on planet Earth is, and I don't know what the tallest person on planet Earth is, but that would be what our range would be, right? So that is an example of a continuous random variable. A discrete random variable that can take on finitely many values is called a finite random variable. So things like rolling a die, there's only 6 possible outcomes. There's no way to get an infinite number of possible. Yeah, so it's discrete, but it's also finite because it's not infinite. And we're going to spend a lot of our time focusing on finite, discrete random variables. Not to say the other ones aren't interesting. So let's go ahead and take a look at this example. So let x be the number of heads that come up when a coin is tossed 3 times. List the value of x for each possible outcome, and what are the possible values of x? Okay, so our experiment is we're going to toss a coin 3 times. We're defining the value of our random variable to be the number of heads in that sequence of 3 things. So we have 3 possible outcomes. Well, we have 3 slots to fill. So how many possible outcomes are there going to be in our sample space? Well, how many choices do we have at each stage? 2. So it's going to be 2 times 2 times 2. So there's going to be 8 possible things in our sample space, right? So let's go ahead and list all of our possible outcomes. So one possible outcome would be head, head, head. We could then have head, head, tail. We could have head, tail, head. And then we could have tail, head, head, right? All right. Well, then we could also have heads, tails, tails. We could have tails, head, tails. And we could have tail, tail, heads. So that was no tails. This was all of our 1 tails. This is the way we could do 2 tails. And then lastly, 3 tails would be tails, tails, tails. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. We've indeed listed all of them. That's not the only way you could list them, right? That's just the order I picked to list them in. And remember, with sets, it's unimportant. We just needed to come up with all 8. So these are the outcomes in our space, right? And we're defining the possible values of x to be the number of heads. So then this one has how many heads? 3, 2, 2, 2, 1, 1, 1, and 0, right? So those would be the possible values of x. So what would be our smallest value of x that's possible? 0. And what's our largest value of x that's possible? 3, right? So we have our 8 possible outcomes, and we'll notice that we have different outcomes that have the same value. And that's okay, right? Because head, head, tails gives me 2, but so does head, tails, heads, and so does tail, heads, heads. Because even though they are different events, they have the same number of heads, right? Because that's all we're counting. So one thing we need to be cognizant of when we're talking about random variables, a random variable is a rule on a sample space. Could I assign a different rule to this same sample space? Sure. What if I made the rule the number of tails? Would that change all of my outputs? The sample space would stay the same, but if I was counting tails, the first one has how many tails? 0, right? What if I defined my rule to be the difference between the numbers of heads and tails? So I'd find the number of heads, the number of tails, and then subtract them. Would that give me different numbers? Yes. So that's a different random variable on the same probability space, or on the same sample space. So remember, there are 2 parts to this. It's not just the sample space, but it's the rule that assigns the numerical value to it. That's x, our random variable. So the sample space is actually our domain. The random variable is the rule, or the function that assigns a value to events in the sample space. So sample spaces can have many random variables. Just like the set of real numbers, how many functions can you define on the set of real numbers? An infinite number, right? X, x squared, x cubed. The domain has very, very little to do with the rules that you can make up on it, aka functions. So keep that in mind. There's going to be a whole bunch of different random variables, so we have to pay attention to what the definition of that is, because it will change our numerical outcomes. All right, so furthering this, if we wanted to then, we could make and organize these things together by their values, if we felt so inclined. All right, we need another definition now. So the pre-image of an output y of a function is the set of all elements x in the domain such that f of x is equal to y. Let's look at a concrete numerical example. So the pre-image is everything in the domain that gets mapped to that element in the range. So for example 4, let's find the pre-image of y equals 4 and y equals 9 if f of x is equal to x squared. So remember, f of x is just a different way to write y. So our rule is y equals x squared. So what would be the pre-image of 4? Well, we need to know everything in the domain x, so we want all x's. Such that f of x is equal to 4, right? So if we do that then, well, we have 4 is equal to x squared. So if we solve that equation by taking the square root, we get x is equal to -2 or x is equal to +2. So the pre-image of y equals 4 is the set -2, 2. Because if I put either -2 or 2 into that rule, what do I get? 4, right? Okay. So the pre-image is just the set in the domain that gives us that output. So there can be more than one thing, even if there's only one thing in our.
So the possible answers?
Yeah, well, they're the things that our rule sends to that value of 4. And so they're in the pre-image because f of negative 2 is equal to negative 2 squared, which is 4. And f of 2 is equal to 2 squared, which is also 4, right? So both of those inputs have the output of 4, which is what we were looking for. All right, so for the pre-image of 9, we would do the same thing. So 9 equals to x squared. We would take our square root once again. So x equals negative 3, or x is equal to positive 3. So then our pre-image would be the set negative 3 to positive 3, right? So now, what would be the pre-image of the set negative 4, or from the pre-image of the set I equals 4 to 9? So we need all of the x values that will get sent into the set 4 to 9. Well, luckily, we just kind of found that. So let me sketch a picture of what we just found. So our rule is f of x equals x squared, right? And we just found that the pre-image of 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the pre-image of 4 gave us 2 and negative 2. And the pre-image of 9, so this is not to scale, gave us negative 3 and 3, right? Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Not to scale, though. So, yeah. Okay. So, we have our 9 and our 4. So then, our pre-image is going to be all of the stuff in between that. So, the pre-image of 4 to 9 would be the set negative 3 to 2 unioned with 2 to 3, right? Because anything between the numbers negative 3 and negative 2 would go between 4 and 9, and anything between the numbers 2 and 3 would also go in between 4 and 9. So the idea of the pre-image is if we know what some outputs are, we just want to find all of the inputs that go along with that. All right. So then if we went back to our previous example where we were talking about this, well, what would be the pre-image of 2? Well, what things had output 2? Here, so what would be its pre-image? Heads, heads, tails, heads, tails, heads, tails, heads, heads, right? So that would be the stuff in our domain, aka our sample space, that went to the value of 2, right? So let's keep building on this idea. So given a random variable x, we can consider the set of all outcomes, the range of a random variable, is a set of numbers. The set of pre-images partition the domain. So if we look back at this example, if we look at the pre-image of everything that's in our range, so 0, 1, 2, and 3, it covers all of those pre-images, partition our sample space. So let's use this. So let x be the number of heads that come up when a coin is tossed 3 times. Find the probability distribution of x. So we've got this that we just found out. So we want to find the probability distribution of this. So the size of our sample space was 8, right? And then we have each of these things. So if we make our table, it's going to look something like this. We're going to have x equals to 0, x equals to 1, x equals to 2, and x equals to 3. So in our probability distribution, we have 1, 2, 3, 4, 5, 6, 7, 8 things. So how many ways can I get 0? 1 out of 8. How many ways can I get 1? 1, 2, 3, so 3/8. How many ways can I get 2? Also 3, 3/8. And how many ways can I get 3? 1, so I get 1/8. So this represents my probability distribution. So according to this random variable, if I flip a fair coin 3 times, my probability of getting no heads is 1/8. My probability of getting 1 heads is 3/8. My probability of getting 2 is also 3/8. And my probability of getting 3 would be 1/8, which seems intuitively to make sense, right? Getting no heads or 3 heads is going to be the hardest, right? Because that would require 3 of the same flip. And getting any mixture of those would be the next most common thing, which is indeed what this shows. So that's our probability distribution for our random variable x. So, like I said, we could come up with a different rule. And if we did that, it would change what our distribution would look like. So, something you may have noticed in our previous table is if you added up all of the values in the probability distribution, what did you get? What's 1/8 plus 3/8 plus 3/8 plus 1/8?
8/8.
Which is 1. Well, that's exactly what happened when we had probability distribution functions in the previous chapter, right? So if x is a random variable with values n1 to n2 through nk, then its probability distribution lists the probabilities that x equals n1, x equals n2, blah, blah, blah. And the sum of these will always add up to 1, because the sum of the entire probability space, or the sample space, always has to be 1. All right, example 6. Roll a fair die. The random variable x is the number facing up. Make a probability distribution and find the following probability. Okay, so we want to roll a fair die, and the random variable is the number facing up. So what are the possible outcomes of this experiment? 1, 2, 3, 4, 5, and 6. Since our die is fair, all of these events are going to be equiprobable. So x equals 1, x equals 2, x equals 3, x equals 4, x equals 5, and x equals to 6. So each of these are going to have a probability. They can happen one way out of 6 possible outcomes. So each of them have a probability of 1/6. So if I were to look at my events, we want the probability that x is bigger than 2. Well, the probability that x is bigger than 2 is going to be all of these, right? So this is the probability that x is bigger than 2. So how many ways can that happen? 4/6. So we want the probability that x is less than 7 but bigger than 4. So less than 7 but bigger than 4, well, that's going to put us, right here. So there are 2 ways, so 2/6 that can happen. And we want the probability that x is smaller than 1. That doesn't exist. It can happen 0 ways, so this is impossible. Because the smallest number on a die is 1. So there is no way to get a number smaller than 1. So the probability of that event is 0. All right. So it's worth noting that the probability that x is bigger than 2 is the same as the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6. Because it's just 2 different ways to say the same thing, right? And those events are all independent from each other, so, or mutually exclusive. So we would get that if we added those up, once again, it's 1/6 plus 1/6 plus 1/6 plus 1/6, which gives us 4/6. Similarly for our other one. So for our event in purple, that we want it between 4 and 6, or 7, right, is the same as the probability that x equals 5 plus the probability that x is equal to 6. Very good. So now we want to talk a little bit about, we're going to be using both capital X and little x. So we want to talk about, well, what is the difference between capital X and lowercase x? So capital X is, this is the random variable. So this is a function. Little x is what? Well, in this previous example, what was little x? 1, 2, 3, 4, 5, and 6, right? We wanted to know, well, what was the probability that x equaled some number, right? So these are going to be the numerical values that are assigned to something. So these are range elements. They're the numerical values assigned by the rule. So they're numbers. We'll do some more examples to help clarify that, but we need to distinguish between capital X and lowercase x. So let's take a look at, we'll try this again. Example 7. So in this experiment, all we know is that an unfair coin is tossed 100 times. The random variable x is the number of heads that are tossed. Use a table to create a frequency distribution. Okay, so our experiment this time, as we said, was we tossed a coin 100 times. We know it's unfair, and our random variable x is the number of heads that are tossed. So if we start looking at the number of heads that were tossed, well, that's going to be our first column, or our first coordinate. So what's our smallest number in our set?
66.
A little smaller, so 65. And let's go ahead and make a table then with those values. So we have 65, and what's our largest value that we have? 71, so 66, 67, 68, 69, 70, and 71. So how many 65s did we have in our table? Just one, and I put that in the wrong place. So let's put it in the right place. How many 66s do we have? 1, 2. How many 67s do we have? 0. How many 68s do we have? 1. How many 69s do we have? 1 and 2. How many 70s do we have? 1, 2. And how many 71s do we have? 2, right? So this is our frequency distribution. How many events were in our sample space? Well, how many times did we toss the coin 100 times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So then, that is our frequency chart, but we want a frequency distribution. So then we would have to divide each of these by the number of experiments. So let's see, 65, 66, 67, 68, 69, 70, and 71. So then we would have 1 out of 10, 2 out of 10, 0 out of 10, 1 out of 10, 2 out of 10, 2 out of 10, and 2 out of 10. So our frequency distribution, once again, what does all of the entries in that table add up to? 1. So this is the same as when we were talking about an experimental or modeled probability versus when we did our previous examples. This is an example of a theoretical probability. So both of these will be helpful depending on what we're trying to do. In some situations, we can come up with theoretical probability models. In some situations, we're going to have to just observe data and come up with experimental or frequency distributions. So that's really the difference between a probability distribution and a frequency distribution, is a frequency distribution comes from observed data from experiments. A probability distribution is derived from theoretical probabilities. So in this case, well, what event or events seem the most likely for this unfair coin?
69, 70, 71, 66.
Yeah, so 69, 70, 71, and 66 all occur with a frequency of 2 or an estimated probability of 0.2, right? One could argue, do you think 10 experiments is enough to really determine a good distribution for this? No, right? We would need more data. We don't have a big enough sample to really talk about what's going on. So, speaking of that, example 8 is going to build on that idea. So this time, we are still tossing an unfair coin. The random variable is still the number of heads tossed. The experiment this time is repeated 1,000 times. The number of heads is grouped into bins or measurement classes. So in the previous one, our bins, if you want to call them that, or measurement classes were all of size 1, which means we were counting just exactly how many heads. Oftentimes, we are going to want to group things together. Like, for instance, if you wanted to talk about salaries at a workplace, you're not going to want to have everybody's salary down to a penny, right? Because then everybody's going to be in their own bin. It makes it really hard to talk about different things. They usually do them in ranges, right? So people make between 20 and 25,000, and then 25 and 30,000, and 30 and 35,000. So those are called bins or measurement classes. So if our sample space contains too many discrete little things, we will group them together to try to group together like data. This type of grouping will help us see patterns sometimes when things are too spread out. So in this example, we created bins or measurement classes of size 5. So we're grouping all of the x's together into those bins. So if there were 60, 61, 62, 63, or 64 heads, they all go into this group. We don't know specifically how many if it was 60, 61, 62, 63, or 64, but we know there were 2 of them, right? So it's basically making the data from the previous example a little bit coarser. But if we had 1,000 of these spread out in really big bins, as you look at the data here, spread out from 60 to 99, that's 40 things. That would be a huge table. That would be really hard to work with. It would also be very hard to communicate that data to people. Bins give us a way to chunk stuff that is human understandable. So now looking at this experiment, it looks like when we repeated it 1,000 times, we only got 2 between 60 and 64. Between 65 and 69, we got 52. Between 70 and 74, we got 835. Between 75 and 79, we got this, and so forth. So, in terms of our probabilities and our frequencies, we need to keep reading. So it says, assign each measurement class the number x that is the midpoint of the bin. So what is the midpoint of our bin 60 to 64? 62, right? Well, 62.5. Because if you add them up, right, we're going to get 60 plus 64. Nope. It's going to be 62, right? We add them up. 60 plus 64 is 124. 124 divided by 2 gives us 62. 65 plus 69, add them up, divide by 2, we're going to get 67, and so forth. So 67, 72, 77, 82, 87, 92, and 97, right? So we now want to create our relative frequency distribution. So using those values, we're going to have 2 over 1,000, 52 over 1,000, 835 over 1,000.
Excuse me, isn't it supposed to be like repeated 10,000 times?
Oh, I think it is. I am missing a 0. 10,000. Thank you.
Yeah, because in the experiment it says that it's repeated just 1,000.
Yeah, I'm missing a 0. So 4328 over 10,000. Because, yeah, those definitely add up to 10,000. 1243 over 10,000. 70 over 10,000. And 0 over 10,000. Yeah, it should have been 10,000. If you add up all of the experiments, the sum of all of those things is 10,000, not 1,000. So that would be our relative frequency distribution of our random variable x. So based on this table, it seems like this coin is pretty heavily biased towards heads, right? Because our biggest number of heads seem to focus around 75 to 79 and 80 to 84, right? So in fact, 43% of the time we got between 80 and 84 heads, and 34% of the time we got between 34.7% of the time we got between 75 and 79 heads. So that would strongly suggest that this coin probably comes up heads, I would say, around 80% of the time, right? Because we got between 75 and 84 heads, if you add those two percentages together, about 77% of the time. So that would seem the most likely weighting for that coin. All right. So, example 9, we want to use an estimated probability distribution from the previous example to calculate these values. So what is the probability that x is equal to 82? Well, based on our table, the probability that x equals to 82, yeah, so we're going to say our probability is 43.28%. All right, so what's our probability that x is less than 80? Well, the probability that x is less than 80 is going to be this group right here. Yeah, 62, 67, 72, and 77. So if we add those guys up, we're going to end up with the following. So 2 plus 52 plus 835 plus 3470 gives us 4,359. So 4,000. So the probability that x is less than 80 is given by these values. By the 10,000. gives us about 43.59%. So the probability that x is less than 80 is this. All right, so now we want the probability that x is greater than 84. So bigger than 84, that's going to be this guy. So bigger than 84 is going to be the last 3 boxes. So that's going to give us 1243 plus 70 which is going to give us roughly 13%. So now we'll notice all 3 of those partition the space, right? So if we add all of those percents together, what should we get? 1. Yeah, or 100%, right? And we can double check that by going 43.28 plus 43.59 plus 13.13, and we get exactly 100% as advertised. So, all right, what is our last one? Well, what's the probability, or our estimated probability, that x equals 97? 0. Yeah, 0. That never came up in our experiment. So the estimated probability that x is equal to 97 is equal to 0. All right. So now we're going to move into 9.2. So Bernoulli Trials and Binomial Random Variables. So a Bernoulli trial is an experiment that has exactly 2 possible outcomes. Called success and failure. So if the probability of success is p, then the probability of failure has to be q is 1 minus p. Why? So what is the size of our sample space? Our experiment has exactly 2 outcomes. What are they? Success and failure. So that means success and failure are actually complements. Right? So if you call your event E success, then E complement is equal to failure. Right? And what do we know about the probability of E plus the probability of E complement? What does that have to equal? 1. So if the probability of success is p, then the probability of failure, which would be q, so p plus q has to equal 1. So we minus p. So q has to equal 1 minus p. It's because the way we've defined this experiment is if there's only 2 outcomes, they have to be complements. And the complement formula tells us that the sum of complementary events' probabilities must be 1. All right. So a sequence of Bernoulli trials is an experiment where a Bernoulli trial is repeated a set number of times. So the last example we were working on in the previous section was a Bernoulli trial. We flipped that coin again and again and again and again and again and again, right? So a sequence of independent Bernoulli trials is a sequence in which the outcome of all trials are independent and the probability of success is the same. So essentially, in a sequence of independent Bernoulli trials, we're keeping all of our parameters the same. So we were using the same unfair coin again and again and again. We didn't swap out the unfair coin for a fair coin. That would change the probabilities, right? We also need to make sure the events are independent. And in that case, what I flipped on the coin last time does not affect what's going to come up next time. That's the gambler's fallacy, right? That if I just rolled a 6, that somehow I'm less probable to roll a 6 again. That's not true. In fact, if you do the conditional probabilities, you would discover that they're exactly the same. That's why they call it the gambler's fallacy. All right. So I want you guys to name a sequence of independent Bernoulli trials. So just think of an experiment that would be an independent Bernoulli trial. Besides the coin toss, because I already did that one. All right, so there's as many examples under the sun that you can think of. What about rolling a die? What if I roll a die and record the number? If I do that 10,000 times, I've just done 10,000 Bernoulli trials. But I would need to define my event to be something, right? Because what are my only two things? So what if I define a success to be a 1, then failure is anything else?
Oh, okay.
Right?
I thought it was only like 2 options.
Well, that is 2 options. But remember, we can change our random variable x to be how we assign the rule, right? So there are 6 outcomes in the space, but if I define success to be 1, then everything else is a failure. Right? So Bernoulli trials can be made out of anything by just defining the event and then the complement of that event. So they're nothing special. So we give them this special name. Well, I shouldn't say they're nothing special. It's not some grand new creation that we haven't seen before. It's just we're giving names to things that we haven't named before. All right. So roll a die. Success. And success. Roll a 1. Fail everything else. So we could do all sorts of things. You could draw a card out of a well-shuffled deck of 52 cards and define drawing a 6 as a success and everything else as a failure, right? And all of those would be Bernoulli trials. And as long as you keep putting the 6s back in and shuffling, they would also be independent. All right, so a binomial random variable is a variable that counts the number of successes in a sequence of independent Bernoulli trials where the number of trials is fixed. So, for instance, if we had a tree diagram that looked something like this, we could illustrate what a sequence of Bernoulli trials would look like as successes and failures, right? So we could have success and then a failure, and then in each branch we would have success and failure, success, failure, success, failure, success, failure, success, failure, success, failure. So this would be, here, would be the event SSS. This would be the event SSF. This would be the event SFS. This one would be the event SFF. This one would be the event FSS. This one would be the event FSF. Down here, we would have failure, failure, success, and then finally 3 failures. Fail, fail, and fail. Right? So in this Bernoulli trial of 3, whatever it is, 3 experiments, those would be our possible outcomes, right? You could have 3 successes, a success, and a failure, a success, failure, success, success, fail, 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 success, success, fail, success, fail, 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 success, and then 3 fails. And that would represent all of the 8 possible outcomes once again. So the interesting thing about a Bernoulli trial, since it's always success and failure, how many branches is everything going to have? 2. Because what are our only outcomes? Success and fail. That's it, right? All right, let's take a look at our next example. Example 2. Suppose that we have an unfair coin with the probability of heads P and the probability of tails, then Q would have to be 1 minus P. Let X be the number of heads you get in a sequence of 5 tosses. We want to find the probability that X is 2. Okay, so our experiment consists of flipping a coin 5 times, right? So 1, 2, 3, 4, 5. Okay. So how many outcomes are there in this probability space? Well, 2 times 2 times 2 times 2. So 2 times 2 times 2 times 2, 5 times. So 2 to the 5th is 32, right? We're specifically interested in what subset of these events? Well, heads, particularly how many heads? So we let X be the number of heads you get in a sequence of 5 tosses. We want to find the probability that X is 2. So one possibility would be heads, heads, tails, 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 right? But as we saw in some of our other things up here, if I was only doing this 3 times, right, how many ways could I have gotten 2 successes? Well, I could have got them here, 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 or, nope, that's it. So 3, right? There were 3 ways to get exactly 2 successes, right? Well, we need to come up with a way to help us count these. So we're going to think back to our counting principles. So what are we arranging? How many heads do we have? Well, in this word with 2 letters, how many heads do we have? 2. And so we can put the head in any one of those 5 spots. And then we can put the second head in some other of them. So how many ways can we rearrange 2 heads in 5 spaces? Well, we're arranging 2 heads, and we have 5 spots to put them in. So is it a combination or is it a permutation? Good. Combination. So what are we going to get? 5 choose 2. We can put 2 heads in 5 spots in 5 choose 2. Wait a minute. Our book uses this notation. 5 choose 2 ways. Right? So then we grab our calculator, and 5 choose 2, 5 choose 2 gives us 10. And we know that there were 32 events in our entire sample space. So the probability that x is equal to 2 can happen 10 ways out of 32. So let x be the number of heads you get in a sequence of tosses. Find the probability that x equals little x. Okay, so let's think about this. What would, if we were going to make a table, which is really what it's asking us to do, it's saying it wants little x equals 0, little x equals 1, little x equals 2, well, we already did that one, x equals 3, x equals 4, and then we only did it 5 times, so we would stop there. So how many ways, so 0 would be 2, 3, 4, 5. Well, 0 says how many heads did we get? If we have x equals 0, how many heads did you get? 0, right? How many ways can you arrange 5 t's? Well, if I switch any 2 of them, would it look different? No. So how many ways can this happen? 1. What's the official answer? It's 5 choose 0, right? And what's 5 choose 0 equal to? 1. So this is 5 choose 0, and that gives us 1. So then, okay, now if we had 1 head, how many ways could we arrange 1 head in 5 spots? Yeah, so that's going to be 5 choose 1, which happens to be 5. 2 we did above, so that's going to be 5 choose 2, which we know is 10, because we already calculated it. So our next one's going to be, how many ways could you arrange 5 heads, or 3 heads in 5 spots? Well, that's going to be 5 choose 3. And what does 5 choose 3 equal to? Also 10. And what about 4 spots? 5 choose 4, which turns out to be 5. And then finally, 5 choose 5 is the same as 5 choose 0. Because if you have 5 heads, there's only one way to rearrange them. And that's going to give us 1. If you add all of those up, what do you get? 1 plus 5 plus 10 plus 10 plus 5 plus 1. And it indeed is. 1 plus 5 is 6. 6 plus 10 is 16. 10 plus 16 is 26. 26 plus 5 is 31. 31 plus 1 is 32. So then, finally, calculating our probabilities, we're going to have 1 over 32, 5 out of 32, 10 out of 32, 10 out of 32, 5 out of 32, and 1 out of 32. So, something that we may have noticed when we were doing this is when we started writing out the strings and how we could rearrange them with success and failures, we got 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. And it counted up. And that told us how many ways we could rearrange each of the possibilities like what we had in this probability tree, right? So here, this is 3 choose 0, 3 choose 1, gave us how many ways we could get 2 successes, or 1 failure, if we're looking at, I should do it the other way. So this one, I should start at the bottom to make this argument. Because we define successes to be this. So this one is 3 choose 3. This one is 3 choose 2. Darn it. Sorry. Choose 3, 3. This one is 3 choose 2, which is we wanted 2 successes. So that's this one. This one had 2 successes, and this one had 2 successes, right? And then our next one that we ran into is 3 choose 1, which is 1 success. And counting our 1 successes, we're here, here, and here. And then lastly, counting no successes was down here. Right? So we noticed that this partitioned and counted our entire probability space, right? So it turns out that this leads to exactly the definition of what's called the binomial random variable. So first of all, I know this formula looks a bit intimidating when we start. This formula is exactly what we just did. It just gives us a formulaic way to calculate it as opposed to going through and counting all of the things individually. So if x is the number of successes in a sequence of n independent Bernoulli trials with the probability of success p and the probability of failure q, which is a 1 minus p, then the probability that x is equal to x is equal to c, so n choose x, p to the x times q to the n minus x. So, for example, if you roll a fair die 5 times, what's the probability that you throw exactly 2 4s? Okay, well, let's do the formula and then we'll do it the long way. So we want the probability that we throw exactly 2 4s. So let's define our success is 2 4s. So then that makes our P. Well, what is the probability of rolling a 4? 1 out of 6. And then that makes Q, our probability of failure, 1 minus 1 over 6, which is 5/6. So, sorry, our success should really just be a 4, because we're going to need exactly 2 of them. So that means we're going to want so then our probability that we get exactly 2 of them is going to be, out of our 5 rolls, so we're going to have 5 choose 2 times our probability of success, which is going to be 1 over 6 squared, times our probability of failure, which is going to be 5 over 6. And we're going to raise that to the 5 minus 2. And then we go 5. Choose 2 gives us 10 times, and I'm going to have 1 over 6 squared times 5 over 6 to the 4th to the 3rd. 5 minus 2, which is 3. So it would appear, according to this, that we would have a about a 16% chance. All right. Next example. By 2030, the probability that a randomly selected resident of the United States will be 65 years old or older is projected to be 0.2. What is the probability that in a randomly selected sample of 6 U.S. residents, exactly 4 of them will be 65 or older? All right, so success is 65 or older, and our probability of that, according to this, is 0.2. So then our failure is going to be 1 minus 0.2, or 0.8. All right, so what is the probability that exactly 4 of them will be 65 or older if we randomly select 6 people? So from our formula, the probability that x is equal to little x is equal to our choose function. We're choosing a subset of 6 people, and little x, times our probability of success is 0.02 to the x, times our probability of failure, which is 0.08, to the n, in this case, which is 6 minus x. And we want exactly 4 people, so the probability that big X is equal to 4 is going to be 6 choose 4 times 0.2 to the 4 times 0.8 to the 6 minus 4 is going to be 2. So let's go ahead and calculate this on our calculator. So we go 6, and we're going to choose 4, and then times 0.2 to the 4th times 0.8 squared gives us the following number. according to this, it would be pretty unlikely, about 1.5%, right? So not very likely to happen. All right, so B says if X is the number of people aged 65 or older in a sample of 6 people, construct the probability distribution of X and plot its histogram. So something that we can do on our calculator that is nice is we actually wrote down this nice formula here, right? Well, we can actually put this right into our calculator. So if we press our y equals, remember, probability random variables are just functions, right? So we can go parenthesis, and we're going to go 6 math choose x, close our parenthesis, times 0.2 to the x times 0.8 to the 6 takeaway x, right?
So we just place the result in the calculator.
Yeah, under y1, so you press your y equals, and then go second table. And then when we look at our table of values here, if you get a negative, it gives you an error. And you'll notice if you go above 6, it gives you 0. Interesting. So then if we go ahead and you should get something that looks like this. Oh, one of those numbers looks a little bit familiar, right? When we asked what was the probability that 4 of them were 65 or older, what did we get? Oh, 0.01536. What is it? It's a corresponding entry in this table. If you add all of these things up, what do you think you're going to get? 1, right? So this actually created the entire probability distribution, right? So then a histogram is just a plot of these things. So you have 0, 1, 2, 3, 4, 5, and 6. So let's go ahead and label this in point 1, point 2, point 3, point 4. So 0 is like 0.26, so it would look something like this. Point 1 would be, or 1 has about a 0.39, so that's going to be all the way up here.
And they would just like put tape or put graph on a calculation and be able to get the actual.
If you graph it, it's going to graph something crazy. There is a way to get our calculator to do it, but it's not worth the effort. There's our 2. At 3, we would get out to 0.81, so that gets pretty small. 4, we're at like 1, so that's extra teeny. And then the last ones are so small I don't think I can actually draw them, so they're just little bars. Right, because they're 0.001, so 1/10 of 1%, and then it's like 1/1000th, 1/10,000th of 1%. So they're both teeny, teeny numbers. So that would be our histogram. So what, according to this, would be the most common, if you randomly selected 6 people, what would be the most common outcome? One of them being 65 or older. And having 0 or 2 of them would be, they're pretty close to each other, 24 and 26% respectively. All right. Part C says, compute the probability that x is less than or equal to 2. Well, what's that going to be? Yeah, so the probability that x is less than or equal to 2, well, that's going to be these guys, right? So that's going to equal 0.26214 plus 0.39322 plus 0.24576. Instead of typing all of that in, we can just grab our calculator, because this is p of x equals 0 plus p of x equals 1 plus p of x equals 2. So on our calculator, you go back to your screen and you just go alpha trace, select y1 goes 0, plus alpha trace, we want of 1, plus alpha trace 2. Putting those into our calculator gives us 0.90, so like 90%, right? Our next one says, compute the probability that x is bigger than or equal to 2, right? Well, bigger than or equal to 2 would be all of the stuff starting at 2 all the way to 6. Well, that would be the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5 plus the probability that x equals 6. And we could indeed type all of that out on our calculator, but this is the complement, so it would be equal to probability that x equals 0 plus the probability that x equals 1, right? So if that's the complement, it's going to be 1 minus probability that x equals 0 minus the probability that x equals 1. So then that's 1 minus y1 of 0 minus y1 of 1. If you added all of those up, you would see you get the same thing, right? So it's not wrong, it's just you can type less if you use the complement. Yeah, if you did it and added them all up, you'll get the same thing. It's just you'll type more. That's the only difference. Because remember, complements just give you a different method to calculate the same thing. It'll never, if done properly, give you a different number. All right. So, this last one is for you guys. All right. So let's go ahead and do this. So we want to know, what is the probability that 2 or more are defective? So then we're going to define our success to be well, there's more than one way to do this, right? So we're going to define success to be defective. And so then what's our probability that it is defective? 0.05. So then Q is going to be 1 minus 0.05, which equals 0.95, right? And we want the probability that 2 or more are defective. So our probability that x is equal to little x is going to be, well, we're choosing 10, so that's going to be 10 choose x times our probability of success is going to be 0.05 times x times 0.95 times 10 minus x, right? So this gives us our function. So what would we want? Well, we need the probability that 2 or more defective, so that's probability that x equals 2 plus the probability that x equals 3 plus dot, 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 all the way out to the probability that x is equal to 10, right? Well, we have our calculator, so this isn't going to be terrible. And there's more than one way to do this, as always. So let's just edit this thing. So 10, choose x. My probability of success is 0.05, and the probability of failure is going to be 0.95 to the 10 minus x. And then I want to add all of those things up. So I can go alpha window, grab my summation, and I want to start at I equals 2 to 10, and I want to add up all of my y sub i's. So we would get this value, and this is probably not the way you would want to do it by hand, because what is this the complement of? What would be the complement of this event up here? The complement is the probability that x equals 0 plus the probability that x equals 1, right? So then 1 minus those would be 1 minus y of 0 minus y of 1. And what do we get? The same thing. So the other thing I want to mention, is this the only way that I could have defined this Bernoulli trial? No. I could have defined my success to be something else. I could have defined my success to be that it was not defective. Then my failure would be that it was defective. You'll get the same answer, right? There is a million ways to cook these problems. So if somebody thinks of it in a different way, as long as you don't break any rules, you're going to get the same answer at the end. Just like if you brute force add all of them up, you're going to get the same answer as if you use the complement.